Hello. We will discuss now multiple linear regression. Multiple linear regression. So, the presentation will be like this. This is a very basic lecture on multiple linear regression. So, as a result, we will give you a conceptual model, what is a regression model and what are the assumptions of regression model, and if possible I will give you the equation for parameter estimation, which will be discussed in next lecture also. So, see this one, suppose you just think of a experiment, where you are interested to characterize the process, or I can say process characterization is the issue. If you recall my that earlier lectures, you know that I have given a process model with controllable factors, uncontrollable factors, with y, the output, input, controllable x, maybe uncontrollable z, and something like this. If you find out, suppose we want to characterize the process with reference to controllable factor, then y is a function of x. So, that is what you want to find out. Now, then y linear equation will be y beta 0 plus beta 1 x 1 plus epsilon. So, this is known as simple linear regression. So, it will be a regression line like this side your x 1, this side is y, and this will be your beta 0, and the slope represent beta 1, and this is your any point on this line is y, that expected value of y given x equal to, let it be x I, x 1 I, this one let it be, or I 1, x I 1, then it is x I 1. Y 1 for the x 1 variable, I is the ith observation. So, what is the value point here, or any point on this regression line, what it will depict? It will depict that y, that is the mean value of y with respect to x equal to x 1. Now, if there are more than one factor, then your equation will be like this. Suppose there are k number of factors. So, factors means k number of, I am talking about controllable factors here. We are not considering z at this moment, let it be. We can include z here also, but for simplicity I am not doing, because our aim is to see multiple linear regression. So, then this equation represent multiple linear regression. Okay. In multiple linear regression, this one, suppose we have three factors a, b and c. Let they are measured with continuous scale, and we are saying x 1, x 2, x 3, and our quality variable is y. So, I can write linear regression like this: beta 0 plus beta 1 x 1 plus beta 2 x 2 plus beta 3 x 3 plus epsilon. So, this is also a MLR, but here what happened, this x 1, x 2, x 3 independent. If there is some amount of dependency between these x, so we can also write something like this: beta 0 plus beta 1 x 1 plus beta 2 x 2 plus beta 3 x 3 plus beta 1 2 x 1 x 2 plus beta 1 3 x 1 x 3 plus beta 2 3 x 2 x 3 plus epsilon. Here you see there are parameters related to the factors or the variables, and this basically this variable x we say independent variables IVs, and y is known as dependent variables. Dependent variable and all x are independent variables. So, if we assume that the independent variable are correlated, so then we are creating some other coefficient which takes care of their correlation part like this. So, you are creating additional variable with the existing variable. So, this is some kind of in the first class I say that this is some kind of mean effects kind of things, and later on we will see these are beta 1 beta 2 are the main effects kind of thing, beta 1 2 these are interaction effects kind of thing. Okay. So, it may so happen that there is 3-way interaction, then beta 1 2 3 x 1 x 2 x 3 plus epsilon. So, and then if I think that there is the nonlinear part, quadratic effect is there. So, slowly the nonlinear part also can be added with this kind of regression equation. For the time being, we will be discussing with this kind of relation or with this. Okay. So, now let us see one example here. Suppose the viscosity of polymer is of importance whose behavior we wanted to assess, and we also want to characterize this with reference to two process variables, reaction temperature x 1 and catalyst speed rate x 2. And suppose we assume that they are linearly related. It may be so that they are not linearly related, but we are assuming that linearly related, and another one is that we are assuming that they are independent, x 1 x 2 are independent in nature, and those things can be tested once the experiment is done over and the data is collected, that can be tested also. Suppose experiment is conducted and you have 16 observations, and with different temperature and different catalyst rate your viscosity values are like this. So, you see that in y there are variability of y values are changing, and this may be because of change in temperature and change in catalyst rate, and if they are linearly related, then we can develop a multiple linear regression. So, the what is the usual procedure? Procedure is like this: find out the interesting variables or the variable of interest. In this particular example, temperature, catalyst speed rate and viscosity. Then identify the response variable, it is the viscosity. Explanatory variable or independent variable, sometimes you say this is temperature and this, and our characterization relationship y equal to function of x. So, then this model linear model, multiple linear model will be like this: beta 0 beta 1 x 1 plus beta 2 x 2 plus epsilon. Okay. So, what is the job here? Our job is to estimate the beta values. What is our job? Suppose we consider this equation. Our job is estimate beta, which is basically a vector beta 0, beta 1 and beta 2 with respect to this equation. With respect to general k variable, beta will be beta 0, beta 1, beta 2 like beta k, k cross k plus 1 cross 1 vector. So, those this will be estimated. We will see later on that we basically minimize the error, a measure. This error will be minimized with respect to all the observations considered. So, that is why we will consider sum square error and minimize sum square error. This will give you this value using ordinary least square, ordinary least square OLS regression, ordinary least square method. Okay, so there can be ML maximum likelihood estimation, but in this case multiple linear both will give you the same final formula. The assumptions are errors are normally distributed, the variability of y is constant across all level of x, which is homoscedasticity. Observations are independent to each other and identically distributed. There is no or little existence of autocorrelation. If you see the linear equation here, so you see y is function of this, and here importantly these x values, they are fixed values, beta 0, beta 1, beta 2, they are constant values. So, this portion is a fixed portion, pattern portion. So, but y is variable. So, the variability part, the randomness part will be captured by error. Okay. So, other way, in the first one, when you are saying that the samples drawn from normally distributed population means y is normal. So, it indicates that the error is also normal. So, error is normally distributed, errors normally distributed. So, if I say epsilon, this is normal distribution with mu and sigma square. Sigma square will be variability, mu is 0. So, it is 0 sigma square. Whatever variability of y is there, that is going to error. So, with reference to simple linear regression, when one variable pictorially can be represented like this. Suppose this is x, this one is y, and this is my regression line. Suppose this is my x1 and this value is x2. Suppose this value is xi, similarly xn values are there. Then what happened? This, as I told you, that y is beta 0 plus beta 1 x plus epsilon here, this is the fixed part. This for any x value, when you find the value on this line, this is basically this portion, this part, this value is this. So, now if I want to find out the expected value of y, then this is expected value of this equation beta 0 plus beta 1 x plus epsilon. So, ultimately this portion for a fixed x value, if it is a fixed value, this is beta 0 plus beta 1 x plus what is the expected value of epsilon, it is 0. So, that is why we said that for this one gives you the expected value of y given x equal to x 1 in this case, or x equal to x I. So, now the 0 that is why this 0 y 0 that is the first part. Second part is that variability, where it will go, it will be variability will be represented like this. So, everywhere for a fixed value of x you can get different value of y, and that variability is like this. So, x I, this variability is like this, x n. So, that is what this is basically variability sigma square, sigma square, sigma square, sigma square. So, we are saying then the first assumption is errors are normally distributed with mean mu equal to 0 and sigma square is the variance. This sigma square is the variability of the y variable. Now, another second one is that common variance for all population, that is this one. Common variance. What do I mean? We are meaning common variance means here first one is errors are normally distributed, second one is common variance. So, for x 1 the y variability, x 2 y variability, when x equal to x I y variability, they will be same. So, everywhere it will be sigma square, that is known as homoscedasticity. Homoscedasticity. So, y's variability across all values of x will be constant, and that will be sigma square. Third one is that whether when you are drawing sample the observations, so every observation they will be independent. So, you have I equal to how many observations? 1 to n observations, x is there, x1, x2 like this, finally y is also there. So, this is first observation, second observation. So, these observations will be independent. Okay. Suppose if I consider y1 to yn, so all those y1 is no way affecting y2 another, they are independent and they are coming from the same population, that is normal population. So, they each of them are also normally distributed with the corresponding population distribution. Here we will go for one population and we draw n number of samples or a sample of n observations, then each of the observations will be coming from that population with parameter, maybe normal parameter mu and sigma square, then they will be this one. Yeah, apart from this, what will happen, because if this y is independent every observation, then the errors will also become independent, and this y's variability, as the fixed portion is coming out, that the variability portion is going to the error. That is why error is having epsilon is having n 0 sigma square variability. Okay. And other one is there should not be any auto correlation, that means independent, if they are independent there is no auto correlation, means y1 is not dependent on y2 or y2 not dependent on y1. As such, yi is not dependent on maybe yi minus k, maybe at any lag, maybe 1 lag or 2 lag, but they will not be autocorrelate. Okay. So, these are the few assumptions, and then what I want to say that next class we will see elaborately, but suppose we say that y is beta 0 plus beta 1 x 1 plus beta 2 x 2. So, like this beta k x k plus epsilon. So, this can be written like this, x y equal to x beta plus epsilon. Okay. And we will see that how what is the x and what is the beta when I equal to 1 to n. So, how this x will be x will be derived, beta will be derived, all those things. Usually what we will see that when I x will be n cross k and beta will be beta plus 1 into k and like this, and finally using OLS regression we will compute beta cap equal to x transpose x transpose x inverse x transpose y, where x is nothing but we have n observations. So, x 0, x 1 like this x k. So, we have constant term for everywhere 1 1 1 1 1, and this will be x 1 1 x 2 1. Suppose there is I x I 1, then n 1, and like this x 1 k, x 2 k, then x I k and x n. Suppose this is x I k and x n k. So, then this is 1 0 to k, so that and it is n. So, n cross k plus 1. This is the design, this is known as design matrix, and beta will be your beta 0, beta 1 2, beta k, this will be k plus 1 cross 1 parameter to be estimated, and y is nothing but that y 1 y 2 to y n, this is n cross 1, this is what is basically the dependent variable observations. So, here in the design matrix you are getting an intercept term where all 1 every row contain 1, and the remaining this portion, this is basically the independent variable part. These are the observed or fixed values for x 1, x 2 and x k at different say observation, bringing you the different settings basically with reference to experiment. Okay. So, fine. So, please keep in mind multiple linear regression is a very important topic for design of experiment, because we will be later using the concept called response surface. So, this response surface will give you the behavior of the y. For example, if I have two factors A, or I can say x1 or B if I say x2. So, depending on you want to change A and B with a purpose, then the y will be the y values may create create something like this kind of surface. Now, what happened for a particular value of A and B or particular value of x1 and x2, you will be having the y value, and if that y value is desirable one, so you will run the process at that x1 and x2 controllable values, or other way you can say factors. So, thank you. Next class we will see more details.